So, in this lecture we shall be looking at some unconventional ways in which a circuit can be designed. Normally when you talk about logic design, the kind of methods that we talked about, we have said that we can use the different kind of gates to implement logic, AND, OR, NOT. NAND and NOR gates are functionally complete, we can use them as well. We have also seen various ways in which the basic building blocks in design like multiplexers, decoders, etc. can be used to implement logic. Now, in this lecture we shall be talking about something called AND and XOR network. This is not very conventional. So, we will be using AND gates and XOR gates to realize logic functions. Let us look into this in a little more detail. So, what we have just now mentioned is that we have already studied various methods of logic design using basic gates and also using functional modules like the multiplexer. But there are many applications. You think of arithmetic, addition, multiplication, this kind of operations. Well, you had looked at the Hamming error correcting codes earlier, so error corrections. There are applications in communication, decoding, encoding, various such applications where we use exclusive OR operations very heavily. So, if you allow not only the basic gates, but also exclusive OR gates to be used in our final circuit, then the size and complexity of the circuit can be reduced to a great extent. So, one classic example, if you recall, is the circuit to generate the parity of a word. Simple exclusive OR of all the bits will generate the parity. Okay? That was one example where XOR gates will be very efficient. Not only that, it is also very easy to test such circuits. We shall consider this AND and XOR kind of representatives in this lecture. Now, one thing I want to just mention here, that I mentioned the example of a parity generator. Let us take a very simple example. Suppose I have a 4-bit parity generator and I use an XOR gate to generate it. So, I can use a large XOR gate or I can use a cascade of smaller XOR gates, they are equivalent, because normally it is much easier to build smaller gates. So, you see, to generate the parity of 4 numbers bits, I need 3 2 input XOR gates, right. So, the hardware is not that much, but now you think I want to implement the same thing using AND, OR and NOT gates in a conventional way. So, what will be my hardware complexity? 4 input XOR. So, what this function is, I just to recall, XOR is nothing but counting or the minterms which corresponds to the odd number of ones. So, in 4 variable function there will be 8 such combinations where the number of ones will be odd. So, in an AND-OR realization, what we will require? We will be requiring 8 AND gates, each containing 4 inputs each, and in the last stage we will be requiring a large OR gate with 8 inputs. And of course, in the inputs we will be using some NOT gates in addition, there will be 4 NOT gates for the 4 inputs. So, you see you will be requiring 8 4 input gates, 1 8 input gates and 4 NOT gates for a conventional AND or NOT realization. but if you use XOR, you need only 3 2 input XOR gates. You see, this is a classic example which shows that XOR gates for some applications can be very, very efficient as compared to conventional logic implementations. Okay. Let us move on. Now, because our subject of discussion in this lecture is AND-EXOR implementations, let us look at 3 alternate ways of expansion. Well, we already talked about Shannon's expansion earlier. Let us look at it like in this way. Consider that we have an n variable function f with variables x1 to xn. They can be expanded just like Shannon decomposition or expansion we talked about earlier with respect to any of the variables. Well, in this example I have illustrated with x1 in 3 possible ways. These are called positive Devio, negative Devio and our familiar Shannon's expansion. Well, here we use 3 notations where f0 indicates the cofactor of this function f where the input variable x1 is 0. Well, earlier we expressed it like this f1 0, but anyway I am showing it only as f0, and similarly f1 which earlier we showed as f1 1, but this f1 means the variable is at 1, and we introduce another function f2 which is the exclusive OR of f1 and f0, right. Now, with this notation the positive Devio expansion says that the function can be written as f0 exclusive OR x1 f2. Negative Devio says it can be expressed as x1 bar f2 XOR f1, and Shannon expansion says x1 bar f0 XOR x1 f1. Now, recall one thing earlier while talking about multiplexer realization, when you introduce the Shannon decomposition theorem, you recall we used a OR here, not an XOR, but here we are showing an XOR. Well, we shall see very shortly that in certain cases OR and XOR can be equivalent. This is one such case. So here I can either write OR or I can write XOR, they will mean the same thing. So, there are 3 different ways in which I can expand a function. You see one thing that if I expand it in this way, for example, let us say Shannon. So, what does this function mean? This function means I will be having 2 AND gates, one x1 bar and f0, one is feeding with say x1 bar, other is fed with f0. The other AND gate is x1 and f1, x1 and f1, and it is XOR of the 2. So, there is an XOR gate. So, you feed this to this and you get the function f. This is an AND-EXOR kind of realization, right. Okay. Now, let us look at some of the properties of XOR, some of which you already know, some of which may not be very apparent, but we will see this. See, some of the rules you already know. The first one, that exclusive OR is associative. So, whether you take the XOR of x and y and then XOR of z or the other way around, it does not make any difference, because ultimately XOR means whether the number of ones is odd or even. If it is odd, it will be 1. If it is even, it will be 0. Okay. The third one is also known, commutative, whether you take x XOR y or y XOR x, it means the same thing. Now, if you take the XOR of any function with respect to itself or any variable with respect to itself, it will become 0. This is important. Like when you have an expression like this, let us say x y z XOR x y z it cancels each other, this is 0. So, this x need not be a variable only, it can be a function also. Any function XOR with itself means 0, and anything XOR with 1 means the complement not, right. Now, let us look at the other two rules which may not be very familiar to you. This one, this is some kind of distributive law, AND and XOR, x and y XOR z is equal to this. Let us take the right hand side, xy XOR xz. So, let us expand it. So, what is XOR? xy and xz bar or xy bar and xz, this is XOR. So, if we apply De Morgan's law, x bar or z bar or x bar or y bar xz. Now, if you multiply out, x y x bar will be 0, x x bar cuts out, x y z bar and x bar and xz cuts out, x bar x and y bar xz. If you take x common, y z bar or y bar z, which is nothing but the exclusive OR of y and z. Okay. This is on the left hand side. So, you see that XOR and AND they distribute over each other. So, as if you have an AND and XOR, you can multiply as if xy XOR xz, you can do this, right. Now, let us look at another interesting rule. It says this x and y, well again x y need not be variables, they can be any two functions. If the AND of these two is 0, then OR and XOR I can replace, they are equivalent. Well, why it is so? You see, if you look at the truth table of a function, let us say this x y or x or y. So, if I say x or y, what is the truth table? This OR says truth table is this, but in addition I am saying that my x y equal to 0, this condition is true. So, x y 0 means what? The AND of x and y is 0. So, AND means what? X y is the AND. So, I am making this as 0. So, I am left with 0 and 1 0, which is nothing but x or y. So, they are same. So, in any just example, you see, if you look at the previous example, let us go back to the previous slide. This x bar f0 x1 f1, you see there is x1 bar and x1 here. If you take AND of these two, it is 0. Therefore, this XOR and OR are equivalent, you can replace XOR with OR, right. This is the basic idea. So, you remember these rules. Fine. Now, let us come to something called Reed-Muller expansion. Reed-Muller expansion is a classic way of implementing a switching expression using AND and XOR gates. This was proposed long back. There are many applications of Reed-Muller expansion and people have been using it since many years, many decades. Now, the idea of classic Reed-Muller expansion is that we use positive Debye expansion, let us say, to expand a given function repeatedly, recursively. So, if you do that, we shall take some examples later. If we do that, then we can get this function f written as XOR of a number of AND terms. There will be all possible variables. Let us say, let us take a very specific example. Suppose I have 3 variables x 1, x 2 and x 3. This is a general expression, that is why this looks complicated. For 3 variables, this function will look like this: a 0 plus a 1 x 1 plus a 2 x 2 plus a 3 x 3, not plus, this will be XORs, this will be all XOR, XOR a 1 2 x 1 x 2, a 1 3 x 1 x 3, a 2 3 x 2 x 3 and XOR a 1 2 3 x 1 x 2 x 3. So, you see all possible values of x 1 x 2 x 3 and their combinations and terms are there. There is only x 1 x 2 x 3 pairs, 2 of them taken together, 3 of them taken together and none of them. So, there are 2 to the power 3 or 8 such AND terms, product terms. They are all XOR together, and this AI's, these A coefficients, they are either 0 or 1. They may be present in an expansion or they may not be present. This is actually what is referred to as positive polarity Reed-Muller expansion. Positive polarity means all the variables appear in uncomplemented forms. Okay? This is the basic idea. So, let us take an example here. Suppose I have a function like this, I want to express this in the positive polarity form. So, what I do? Well, here I already know the XOR rules we saw in the last slide. This x 1 bar we can write as x 1 exclusive or 1, x 2 bar we can write like this, x 3 bar we can write like this. Well, why we are writing like this? Because this bar we are eliminating, we want to use positive polarity only. So, this x 1 bar we have made it x 1 because XOR 1 means complement. So, we have eliminated the bars like this, and if you put it here it will be like this, and you know that this XOR is distributive over AND, you go on multiplying. So, I have skipped a step, you can do it like this. The first two, for example, if you multiply by x 1, so it will be x 1 x 2, x 1 and 1, XOR x 1, 1 and x 2, XOR x 2, 1 and 1, XOR 1. This will be the first term, and x 3 and 1 remains. Now, if you multiply again like this, you will get, you see x 1 x 2 multiply x 3, you get this, x 1 x 2 and 1, you get this, then x 1 and x 3 you get this, x 1 and 1 you get this, x 2 and x 3 you get this, x 2 and 1 you get this, and finally 1 and x 3 you get this, 1 and 1 you get this, right. So, you see for this function ultimately whatever you get, this is your positive polarity Reed-Muller form, all variables are uncomplemented, right. Okay. Now, the point is that sometimes we may not require all in uncomplemented form. So, you can have a combination of uncomplemented and complemented form, but you can enforce that some variable say x 1 will appear in only one form of complementation, like x 1 will always be uncomplemented, x 2 will always be complemented, x 3 will be uncomplemented, like that. If you have that kind of a restriction in place, then you can have something called fixed polarity Reed-Muller expansion. Here we can use a combination of positive Devio and negative Devio kind of expansions, where as I said each variable will appear in either complemented or uncomplemented form, but not both. Okay. Let us take an example. Take a function like this, where there is a term x1, x2, x3, x4 and there is a term x1 bar, x2 bar, x3 bar, x4 bar. Let us try to arrive at a mixed kind of a Reed-Muller expansion for this. The first observation is based on one of the rules. You see this x1, x2, x3, x4, this term, and the other one x1 bar, x2 bar, x3 bar, x4 bar. If you take the AND of these two, because there is a variable and complement, they will become 0. This is 0. So, according to our previous rule, if x y is 0, then we can write x plus y and x XOR y as same. Okay. So, the original function was OR, I can replace it by XOR because their AND is 0. Okay. The product terms are disjoint. Now, let us look at the steps of expansion. Now, what we are doing? We are applying, or we are wanting x1 and x2 to be in the uncomplemented form and x3 and x4 in the complemented form. So, what we do? For the first term, because x1, x2 are already uncomplemented, we leave them as it is, but x3, x4 we want in complemented form. So, x3 we replace by this, we bring in a bar, and x4 we do this, we bring in a bar, x4 bar. Similarly, for the other side, x3, x4 bar are already bar, so we leave them as it is, but x1 we make it uncomplemented, x2 we make it uncomplemented. Then using the distributive law, we go on multiplying x3 plus this and this, if you multiply you get this. If you multiply this and this, you get this. Now, straight away you multiply this with this, you finally get x1, x2, x3 bar, x1, x2, x4 bar, like this. You see, you get a Reed-Muller expansion where x1 is uncomplemented everywhere, x2 is uncomplemented, x3 is always complemented, x4 is always complemented. So, you have a fixed polarity Reed-Muller expansion where the complementation can be either complemented or uncomplemented, but not both. Okay. This is what you can have. Now, let us talk about two level AND-EXOR realization. So, the function that we just arrived at, the function is like this. So, in order to implement it, what we need? So, how many product terms are there? 1, 2, 3, 4, 5, 6. So, we will be needing 6 AND gates, first AND gate will be having 2 inputs, second one will be having 3 inputs, third one also 3, fourth one 2, this is 3 and this is 3, and you will have to take the XOR of all of them. See, there are 1, 2, 3, 4, 5, 6. So, one way is to have a large XOR gate with 6 inputs and connect the output of these AND gates to them directly. But as I said, a large XOR gate can be difficult to manufacture. So, what we well, just another thing is that for the input stages you may need some complementing. The X3 and X4 you will be needing 2 NOT gates to complement X3 and X4. So, you need 2 input AND gates and 4 3 input AND gates and 1 6 input XOR gate. Now, what I am saying is that in general, you see, this is a general expression. For some function you may also have a term 1 XOR something, right. So, a general circuit will look like this. So, you can have a chain of 2 input XOR gates. This is an alternate way of implementing. And here, well, for this case you can set it to 0, but if it is 1, then you will be put it to 1. So, the advantage is that you can use small size XOR gates, but the drawback is that the delay will be more. The total delay will be a cascade of these 6 XOR gates, right. Okay. This is what we are mentioning, that instead of a single large XOR gates, we can have a cascade of such gates also, right, in general, right. So, let us work out a complete example here. Suppose we want to find the Reed-Muller expansion for this function. There are 4 true minterms 0, 3, 5, 6. So, if you carry out minimization, you will see that your minimized form of the function will be this. There are 4 product terms. Now, one thing you observe, that there is between each pair of product terms, if you take AND, it will be 0. So, this OR can be replaced by XOR, that is the idea. Okay. So, the first thing is that because they are disjoint, these product terms, there is nothing in common, but let us say if you had 2 product terms AB or BC, then you could not have done that, because AB and BC have something in common. AB and BC is not 0, but if you had AB plus B bar C, then you can replace plus by XOR, right. So, here first step is you replace this OR by XORs. Then suppose I want a positive Reed-Muller form. So, all variables uncomplemented. So, wherever there is not, so x1 bar I replace it by this, x2 bar I replace by this, x3 bar, similarly here x1 bar, x2 bar, and here x3 bar. Then I go on multiplying, like in the method I mentioned earlier. We simply multiply this part. This part is straight away multiply. This red first term gets like this. The second term blue, it becomes like this, x2 x3 XOR x1 x2 x3. The green term become this brown term becomes this x1 x3 and x1 x2 x3, and green term becomes x1 x2 and x1 x2 x3. Now, you see I have an XOR of so many terms. So, now you can apply that rule that any function or subfunction XOR that same subfunction is 0. So, I can cancel them out. So, let us see which are the terms that are getting cancelled out. You see I can get one x1 x2 x3 here and one x1 x2 x3 here, they get cancelled out. So, one x1 x2 x3 here and one here, they get cancelled out. This x1 x2 and this x1 x2 cancels out. This x2 x3, x2 x3 cancels out, and finally x1 x3 and x1 x3 gets cancelled out. So, most of the terms are getting cancelled out, and what you finally have is only one XOR XOR, XOR x2, XOR x3. So, the AND XOR, you do not need any AND gates for this example, you need only XOR. So, it is a very simple form of an expansion. So, with this we come to the end of this lecture. You see what we discussed in this lecture are some, as I said, unconventional ways in which you can represent some functions using AND and XOR gates. We saw how we can realize any arbitrary function using Reed-Muller means expression form either in uncomplemented variables forms or in so called fixed polarity form. Some variables are complemented, some variables are uncomplemented. So, the advantage is that for some functions it can lead to very small realizations, and also later on we will see that when you design a circuit, we also may want to test whether this circuit is working correctly or not. So, for this kind of Reed-Muller circuits, testing becomes very easy, but this we shall be discussing later. Thank you.